need to have at your disposal. So radical stability. Just recall, tertiary radicals are more stable than secondary, more stable than primary. These are much more stable than methyl radicals. Okay, well, my camera is going to focus. I'm going to make it focus. That's right. Okay, so this general trend you need to be able to understand and recognize, and today I asked you to apply it to a specific problem, right? And anticipate what's the best proton to pluck off a more complex molecule, and I suspect you guys did well on this. Okay, so the other thing we did in our quiz today was look at more complex molecules, and I asked you to do propane. So now we're going to look at butane. Oh, I asked you to do pentane, which is 5 carbons. We're going to do butane. And if you had trouble with the pentane question today, this is a good chance for us to remedy that. Reaction conditions might look something like this, or sometimes chlorine is drawn right next to this molecule with a plus next to it, but this means the exact same thing as the reactions we've been looking at thus far. And the first question, if you see a problem like this, that I would ask you or that you should think is to try and anticipate how many unique products there are, right? How many unique products do you anticipate for this particular reaction? And the first thing we can do is sort of look at this particular molecule and find unique hydrogen atoms to pluck off in this radical reaction. The first thing we can do to save half the work here and save some time for ourselves is to cut the molecule in half. And we can see that there's a methyl group or a primary carbon, and there's a methylene group or a secondary carbon, and then these two are repeated on this side. So there isn't going to be a chlorine product here, 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 and here that are unique, really just here and here or here and here. We'll either make 1 chlorobutane or 2 chlorobutane, but we won't make anything such as called 3 chlorobutane or 4 chlorobutane, because those are the exact same molecule as 1 and 2 chlorobutanes respectively. The other thing we're going to ignore here for the time being is stereoisomers. All 3 of these hydrogens are identical, and so I guess I have some time on my hands today. We'll do something a little bit different than what I had planned. So I'm just going to quickly draw out the monochlorination product of butane at the primary position. And it doesn't matter if we put chlorine here, here, or here. This bond freely rotates, and so it doesn't matter which one we pick, they're all equal. This compound only has one name. It's 1-chlorobutane. There's a slight subtlety at the secondary position. For us, I really just want us to focus on unique constitutional isomers. And so there's 2 different hydrogens here. If I replace one with chlorine, this would be 2-chlorobutane. So these are the official products, but technically these 2 hydrogens aren't exactly the same. You might look at yourself and scratch your head, but they look the same to you. Technically, these 2, if we put chlorine here or here, this becomes a chiral center, and we could have R or S in this type of problem. Okay, I'm not going to go to that level with this. We don't need to use R or S again for a little while. We're going to have a little pause in that. But technically, if we put chlorine here or chlorine here, if you think of this as being wedges and dashes, right? If this is a wedge, you can draw this right onto your own notes, right over what I've drawn. Right? If this is a tetrahedral carbon drawn with lines, wedge coming out, a dashed line going back, this would be a chiral center. And so it does matter if we put chlorine here or here. But we're going to ignore the stereochemical aspects of this reaction. And when we think about this, we're going to ignore R and S. We're just going to focus our attention on unique constitutional isomers. We'll ignore stereoisomers. They do exist, but we're just going to ignore them. Okay, hopefully that makes sense. If you missed that or are having trouble with R and S, don't worry, just leave it for now. It's not necessary. Our goal here is when you see this molecule that you could identify correctly that you could put chlorine here or here, and that would give rise to 2 unique products. I'm going to rewrite the same reaction here again. Butane. I'm going to put a dotted line in the middle. And we'll write plus Cl2 is the more traditional way, and heat, just like that. And we could use UV light in place of this, or heat. These are secondary and primary carbons, respectively. And you should practice on your own for this, the first propagation steps. I'll leave a little blank here for you, first at the primary position, and then at the secondary position, and I'll leave one box for you to fill in later. And I'm going to do the second propagation step, and what I mean by that, in the second propagation step at the primary position, we've made a radical. So this is going to go up here in the box, and I want you to work out this mechanism on your own later, okay? Or if you're really bored listening to me and you can keep up, fill it in now, but it's okay to do this later. It's just practice. How do you get to here with Cl radical, okay? And in the second step of the propagation, we know mechanistically that we need one electron here, and this gets us to our product at the primary position, and we regenerate a Cl radical. Okay, and I want you to do the same thing for the second propagation step. You would draw in butane, you'd be plucking off a different hydrogen atom with chlorine radical, and what you would get to, if you get through that step successfully, you get a radical that looks like this. Secondary position, chlorine will be here, and we know that this radical wants one electron. It gets it from this particular bond, and we get to a complete explanation of how the second product is formed in this reaction. We also reform chlorine radical. That's not so important for us. So we're going to get back today and talk about this product distribution and yield issue that we got into yesterday. If we were just looking at a pure statistical point of view, what should the product distribution be between 1-chlorobutane and 2-chlorobutane? Well, we can go back to our original molecule here, and we have a 3-to-2 ratio of primary hydrogens to secondary hydrogens. Or if you add up the whole molecule, we have 6 primary hydrogens and 4 secondary hydrogens, but if we reduce that down, it's still 3-to-2. That's the ratio of primary hydrogens to secondary hydrogens. Okay? And we saw yesterday with propane, something a little strange happened. This is what the absolute number of hydrogens there are, and if the reaction didn't care about primary position or secondary position, then we would have a 60% to 40% yield here. When this reaction is actually done in a laboratory, we get 30% of the primary product and 70% of the secondary product, and chlorine has a preference. Energetically, it's preferring the secondary position, even though statistically there's far more primary hydrogens. And this difference or statistical difference is exactly and directly related to carbocation stability. The secondary carbocation is much easier to make than this primary carbocation, and that's really the focus of our discussion today, digging a little bit deeper into this particular issue, right? Why these distributions come out this way. These yields, please don't memorize them. You can't calculate them. These are experimental values. This 3-to-2 ratio, I calculated that. That's easy enough. There's 3 primary hydrogens for every 2 secondary hydrogens. Or if you like 6 primary hydrogens to 4 secondary hydrogens, I won't disagree with you on that point. Let's do this again for a different molecule. This is N-butane. We're going to take isobutane and see what happens with isobutane. Isobutane has another name. So this is isobutane, or it's 2-methyl propane. Okay? And we're going to think about what happens when we do radical monochlorination with this. And the question is, how many unique products do we anticipate over here? I want you to think about it, and for a moment, see if you can draw those unique products on your own. Again, if I was in class, I'd be walking around looking over your shoulder at what you're doing, but digitally, that's impossible. So draw all the unique products you think there will be. First, figure out, looking at this molecule, how many unique positions are there? Once you figure out how many unique positions there are, you know how many products there are. So if you think it's 3 unique positions, then you should draw 3 products, and you should draw all of them. Then when you draw your products, compare them to one another and make sure they're actually different. You could make a mistake.